Right. Hi, Chris. Hi, Justin. Hey, Omar. Ugh, what is that? Those are hats. Ugh. Hi, Sarah. Good morning. Itamar. All good. All right, all good to you too. Yona, a very good morning to you. Caitlin, good morning. Good morning, Marcelo. Good morning, Ainava. How's it going, guys? Oh, that's very nice. For those of you who are just joining in, we're going to start at 10:03, which is in around 3 minutes. All right, 10:03 for part 3 of the lecture. Get it? Sarah, nice of you to ask. This is, oh my God, it smells like perfume. It's a green oolong, and it's one of the only oolong teas produced in Japan. Traditionally, oolong teas are made in Taiwan and China. And on the whole spectrum of things, it is a very green Japanese. I'll show you what it is here. Okay. That. Yum. And if you can see, I'm going to try and show you. You can tell it's a very green oolong, and it's only lightly oxidized. Because if you look at the leaf, there's red on the edges, but the whole leaf itself is not red. It's still mostly green, right? And that's what keeps that kind of like, it's closer to green tea in flavor, but there's so many floral notes. Oh my goodness. This is definitely one of my favorites. Not, but my favorite's still the one from yesterday. That's the one I have to share with you guys. So, 2 minutes left. Around 13 people in the stream. That's cool. Good morning, Atune. I can tell which one of you are using your Bronx Science emails for this, because I'm pretty sure the ones using your Bronx Science emails have, you're the ones who your names are in all caps, I think, in the chat, right? So the only one who's using their real account is this howdy person. Hi, Dimon. We missed you yesterday. Where were you? Of course I did. You're a very vocal presence in the chat, Dimon. You were on your way to becoming a mod. Not anymore. Understandable. I hope you stayed safe while you went grocery shopping. Yes, Mr. Ross is a moderator, but he hasn't had to exercise his powers because you guys are so well behaved. All right, it's 10:03. So before we go over part 3, let's go over the homework, right? Let's see. So I'm gonna classwork, week 2, it's loop rule. Uh-oh. What is this? Only 30 of you turned it in. Do I want to see who's turned it in? Oh no. Oh no. I won't call you out, but you guys know who you are, and you guys need to do this, right? Because if you do this, if you move on to the next lecture without having done it, right, it's not going to make too much sense. All right, so let's look at the very first one in the upper right. I'm, just for convenience's sake, always going to start at the battery and go clockwise. Then in the bottom resistor, I will lose 5 volts, right? So in that whole simple loop, it's pretty simple, right? I have a net change of voltage of 0, okay? Moving on number 2, just on the very right, I'm gonna start above the battery, and I will, actually, let me start below the battery, okay? So I'm gonna go clockwise, I lose 20 volts, and then I'm gonna take the right branch and I lose 10 volts, so I've lost 30, and then I come all the way back to the battery, which means in the battery I need to gain 30 volts, right? I'm gonna gain 30 volts in the battery, and then if you look at the mystery resistor, I will also, then I would have to go, I would have to lose 10 volts, okay? Now let's take a look at the number 3. I'm going to start on the left side of the battery. I'm going to gain 40 volts, going to go clockwise. Let me just take the bottom branch. I lose some amount of voltage, and then I come all the way back up to the battery. So if that resistor was the only resistor through which my electron traveled, then through that resistor, I need to lose 40 volts. Okay? Now, if I lost 40 volts in that lower branch, let's take a look at what happens if I travel through the upper branch. I gain 40 through the battery, I go through a mystery resistor, I lose 10 volts, and then I come back to the battery. So that means in that mystery, the top mystery resistor, I'm losing 30 volts. Okay? Any questions so far when we're going over all three of those? I'll wait a little bit because I know there's a little latency. All right, Itamar, what's the question? And if anyone else has a question, don't feel free to ask as well, please. Physical law, or is it just a good rule of thumb so you don't short circuit? No, it's a rule that every circuit will follow. Like if an electron returns to its original place in a circuit, it's not allowed to have changed its energy in some way, which means it's not allowed to have changed its potential in some way, right? Is it a good rule of thumb so you don't short circuit? No, it's backwards. Because we know these things don't short circuit, and the current doesn't get faster and faster and faster and faster, and the electrons don't get faster and faster and faster, then that's how we know the loop rule is true. Okay, in loop rule, net electric potential must be zero. Yes, well, the net change, the change in electric potential must be zero, right? I don't know like what the actual values of potential are, but I know once I return, the change of potential will be zero. Let's move on to 4. Whoa, that's funky, huh? All right, so I'm gonna start again below the battery. I'm going clockwise. I lose 4 volts. I take the right branch. I lose 4 volts. I come back to where it's all the current is concentrated in one wire, and then I lose 3 volts and I lose 5 volts. So in total, I've lost 16 volts, which means in the battery, I'm gaining 16. Right? So now let's begin above the battery. So above the battery, I'm going clockwise. I gain 16 because now I want to look at the left branch, right? So I gain 16. I lose 4. I take the left branch. I lose a mystery amount. I lose 2, and then I lose 5, and I lose 3, and I lose 5. So all in all, I have lost 14 volts before I go to the battery. But in my battery, I gain 16, which means in that mystery thing, I have lost 2 volts, right? You guys should now be recognizing a pattern about the drop in voltage. Yes, it is conservation of energy in a nutshell. Yes. You guys should be noticing a trend. Anytime I have a parallel section of my circuit, what I can say about the voltage drop in the whole wire, in the whole second wire, the whole first wire, the whole second wire, what can I say about the voltage drop when they're parallel? Not about the individual elements, but just the total voltage drop when I go through a whole wire and then the total voltage drop. All right, feel free to put it in the chat, all right? We're going to be going over that a little bit soon, but let's go over number 5 first, okay? Whoa. So number 5 is really funky, okay? So the cool thing about number 5 is that, that's really funky, huh? I'm going to show you something really cool. Are you guys ready to see something really cool? All you got to do is look in the mirror. No. Okay, so I'm going to draw a circuit right now, and I'm going to show you when I'm done drawing it. Okay, all three of the circuits that I've shown you are equal. These are all the same, right? There are just a lot of different ways to represent three resistors in parallel, right? There is a fourth way to do this, and it's to draw the bottom two like paired up like this one, kind of like a parentheses in math. Like I don't really care, right? So what I'm basically trying to show you is that for number 5, all three resistors are in parallel, and just like a lot of you have astutely noted in the chat, and just like in your heads, all branches in a parallel section of a circuit have equal drop in voltage. And that is a hard and fast rule, okay? And what that says is something really easy about number 5. That means number 5, every one of those resistors, you lose 9 volts across each of those resistors, okay? It's one of the most important rules you have to pay attention to in physics, right? Like, when I have a parallel section of the wires and stuff, like the voltages are equal, and the way you derive that is through the loop rule, right? So if you ever want to like ask like, hey, why is that true? Because I know a lot of textbooks don't really go over why that's true, all right? Now you know it's the loop rule, right? So like you say, no matter which path I take, I need to lose the same by the time I'm here, right? Otherwise, depending on the loop I pick, then I will lose a different amount of voltage. So like the two branches, they need to have the same voltage drop, okay? All right, cool. So that's like the homework review. And now we are gonna look into something even cooler. All right, so this is part 3 of our 3-part lecture series on our introduction to circuits, okay? This is Ohm's law, okay? So before we get into Ohm's law, okay, let's see. No, this is fine. This is fine. Ohm's law relates the. So anytime I have Ohm's law, there's a lot of different ways to conceptualize Ohm's law, okay? And I think one of the best ways is that it tells the story of what's happening inside a resistor, all right? What happens inside? All right, so I want you to write that down in your notes, all right? There's a lot of different ways to conceptualize Ohm's law. A lot of resources out there incorrectly talk about Ohm's law in terms of the battery, the voltage of the battery, but that's really not what that's not the case. Okay, so what do I mean? I'm saying anytime current goes through a resistor, right? I have a resistor. Anytime I have some current flowing through, okay, I experience a loss or drop, right? So this is a drop of voltage or potential difference, okay? So, I just tripped. When that happens, there is a really strong formula that that you can relate between all three of these, and I'm just going to give it to you. There's if we were in a lab, we would have derived this together, okay? But we can't, unfortunately. Let me show you the basic lab setup then, okay? So the basic lab setup would be, we have a source of voltage, okay? This is our basic lab setup, right? So I have a source of voltage, I have a resistor, and then I have this ammeter. And what this ammeter does, yeah, so no custard, we're gonna do this. This ammeter is here, and what that ammeter does is exactly what it sounds like. It measures the current, right? So this ammeter measures the current traveling through the resistor, okay? This voltmeter measures the voltage drop across that resistor, right? And what I do is I crank up the voltage of the battery. When I crank up the voltage of the battery, the current increases as well. That's what I'm really doing. Why do I expect the current to increase if I increase the potential of the battery? Because it means when my electrons go through here, then they're gaining more and more kinetic energy, right? The more voltage gain they have, the more kinetic energy they gain, and the faster they're moving. So I'm basically increasing the current. So when I crank up this voltage, what I'm really doing is I'm increasing the current. And then I can also measure the drop in voltage here. I also know that voltage is going to increase as well, because this voltage should equal this voltage, right? What I gain here, I need to lose here, right? So remember, I don't really care which one I choose as my independent or my dependent variable, okay? But I do care about where I put things on the axis. And if I measure the voltage drop of that resistor on this axis and the current on the x-axis, here's what I'm going to get. What shape is that? Oh, I don't know if you guys can see. I think only those of you who are on full screen can see. Well, let me make it a little bolder. Oh, wow. Oh, geez. Right? What kind of relationship is that? Oh, my gosh. It's a line, right? So what we've just proven is, proven. Is that the voltage drop across a resistor and the current traveling through the resistor are linearly related, right? So they are linearly related to each other. And I kind of hope that makes sense, because you should think that, the larger my voltage drop, right? The larger my voltage drop is the more energy that electron lost while it was traveling through the resistor. And if it lost a lot of energy before it hit the resistor, that means it had a lot of kinetic energy before it hit the resistor, which means that it was traveling very quickly before it hit the resistor, which would mean it has a big current, right? That's how I relate that. And what Ohm's law really says, and you got to write this down, and this is super important, V equals I R. Right? So now I know that V and I are linearly related. And which lets me kind of say, well, how do I find R from this graph? It's simply the slope. Right? Because y equals mx, right? If I'm saying V and I are linear related, then the R is the slope. Sarah, what would you like me to explain one more time? Why they are linear related? We don't know why they're linear related, right? That's something we would have found in the lab together. Like, as I increased my current, I would have measured the voltage drop across the resistor, and you would have been able to see that it's linear, right? That's like, why is it? Because that's what we observed. That's a rule that the universe plays by once you observe it a lot of times. If there is a loss of voltage because of the resistor, then which V do we use in Ohm's law, the initial or final? That is such a good question. Ayanava, this V is change in V. The real formula should say change in V, but the problem, or like the drop in V, but we always write it as V equals IR because physicists use both V to represent like actual potential and also V to represent voltage, where voltage is like a potential drop. It's really imprecise. I don't know why they don't use this. Yeah, I wish I could tell you, right? So whenever you see V equals IR in like the Ohm's law notation, just know that this isn't a real V. It's change in V, right? So this is what we really mean by change in V. V. It's like, right, change in V, but the way it's written in almost every resource is that it's not, right? Okay. You make sense. All right. Where do I put this? Oh, I should say paper. I'm on my last pad. Okay, hold up. Okay. All right. So let's move on to some, you betcha, example problems. Okay. I'm going to start off with a very simple circuit. Okay. So you guys should be drawing this in your notes. Voltage. Okay. All right. So in this very simple example, so easy that you're not going to get a problem around this level of difficulty ever again. Okay. My battery, I gain 10 volts. This resistor has a resistance of around 2 ohms. Okay. I'd like you to calculate the current running through the resistor. All right. And while you do that, I'm just gonna do my second steeping of this Kawaakiri Oolong. Okay. The first thing you should have done, so here, Can there be a negative change in V or a negative current? No, we're always talking about the magnitude of the drop in the current. But there can be a negative as well. But for all intents and purposes, our circuits, I'm not going to pay attention to that right now because everything is going in one direction. All right. I think in AP Physics C, you're going to have to pay attention to like the sign of the voltage, like whether if I gain it or I lose it and stuff. But here, it doesn't really matter. Okay. So absolute value, exactly. But tune, anytime you hear the word, and this goes to all of you, anytime you hear the word magnitude, that's asking for the absolute value, right? Okay, so here's how not to do it. If I have V equals IR, and I say, oh, the battery's 10 equals I times 2, and I is 5 amperes. Right? That's the correct answer, but it's not the correct way to arrive at the right answer. All right? Because remember, Ohm's law tells the story of what happens inside a resistor. So this V needs to be the drop in voltage of the resistor. It is not the gain of voltage in the battery. Okay? Big difference. Big difference. Okay? So before you even plug in anything, I need to say, oh, my voltage drop was 10 volts as well. All right? You might think that that's really silly, but when we get into things with, for example, more than one resistor, then I'm going to really need to talk about what's happening on each individual resistor. Okay? Now, hold up. This is done steeping. I got to pour it out for a second. Okay, very nice. I want you to smell this, everyone. It smells like flowers. And a little bit of grass. Okay, so I'm running out of ink, but I'm not gonna be wasteful. I'm gonna tough it out. Okay. All right. So let's move on to an example where it would be really important to pay attention to the voltage drop across a resistor rather than just the voltage of a battery. Okay, the voltage gain of the battery. Okay, so I'm just doing this so you can see my face and it's just not cut off anymore. All right, so I'm gonna make a circuit now. Oh my goodness, I want you to draw this too. Boom. I have 2 resistors in series, not parallel, right? So it's 2 resistors in series. Let me use the exact same battery. So voltage gain is 10 volts. And let's call this a 2 ohm resistor. And do I want to make this the same or do I want to make this different? I want to make this different, okay? So let's call this 3 ohms. Okay, so even before we begin, I want to go over a couple of things that we should already know, okay? So if I gain 10 volts here, whatever I lose here needs to be 10, right? I don't know if it's a drop of 5 and a drop of 5. I don't know that, right? I don't know, or if it's a drop of like 6 and a drop of 4, a drop of 7, a drop of 3, a drop of 3, and a drop of 7. Who knows? But I know their drops have to equal 10. All right. So let's draw that. Right. So I'll call this resistor 1 and I'll call this resistor 2. I know that the drop across resistor 1 plus the drop across resistor 2 equals 10 volts. Okay? I also know that the current running through the first resistor is equal to the current running through the second resistor because they're all on the same branch, right? So whatever, think about it like a river, right? Like if I'm like upstream in the river and someone else is downstream, like it doesn't matter. I never want to think about, oh, this uses up some of the current before it gets to there. No, okay? Because first of all, in these types of circuits, we like to assume that the direction doesn't matter, all right? It's going to behave the exact same way no matter which direction it flows. And secondly, if you use the river analogy, like any water I use to power like a wheel or something is gonna move past that wheel, and it's still gonna affect this wheel too, right? Like a paddle wheel. So all the water this takes in, it spits it out, and then this one is, I mean, it's gonna get some backwash, but it doesn't really matter. Like this is gonna get the same amount of water that this got, right? So the currents are exactly the same. So once I know that, and I also know, check me out, right? That V1 equals I1 R1, and V2 equals I2 R2. What I have is a system of equations, right? I have 4 equations. Holy moly, okay? So the first thing I can do is just set one of these equal to, let me put them all in terms of I1, okay? I mean, in terms of like the things that go through the first resistor, okay? So I know that V2 is 10 minus V1. So I have 10 minus V1, and this is equal to I1, because I know I1 is equal to I2, and this is equal to 3 ohms. And I also know that V1 equals I1 times 2 ohms. And now I can solve for I1 and V1, okay? I'm going to do that just by saying 10 volts equals 5 ohms times I1. And I know I1 now is equal to 2, right? So the current traveling through this whole circuit is 2 amperes. 2 amperes, 2 amperes, 2 amperes. At every point I have 2 amperes, right? So I know I1 and I2 is equal to 2 amperes, okay? And if I know the current is 2 amperes, then I know here I have a 4 volt drop, and here I have a 6 volt drop, because the voltage drop is just I times R, the current times the resistance. And if I'm 2 amperes everywhere, then 2 amperes times this is 4 volts. 2 amperes times 3 ohms is 6 volts. Okay? Wait, after the current travels through the resistor, does it go back to its original current level? Yes, always. Even inside the resistor, it is 2 amperes as well. Everywhere is 2 amperes. Think about it as like a lazy river, okay? If you guys don't know what a lazy river is, it's like a pool, but it's shaped like a river, and it's like a flow, and people can ride in like tubes in the lazy river. Every person in the tube, assuming they're not like a rebellious 7-year-old who's like wreaking havoc, is drifting at the same velocity, right? That's what happens in a circuit as well. Every electron is kind of drifting at the same velocity. Okay, so I have 2 amperes everywhere, basically. Yes, that's a very simplified model. Yes, you are correct. So these electrons like gain and lose energy, but what happens is like they kind of push the ones ahead of them when they gain energy. So like the whole system as a whole gains the energy, and loses the energy. It's not just one electron that's speeding up, slowing down, right? So like when one electron gains energy through the battery, then what happens is that it gains that energy, but it gives it to every other electron in the circuit just by this chain reaction pushing, all right? And when an electron loses that kinetic energy through a resistor, it not only slows down, but every electron slows down because the ones behind it run into it, and it causes like a really long chain reaction car crash, basically, right? So that's what I mean. Like, yeah, it's easy to think about. It's a lot easier to think about one electron traveling through this loop and like speeding up when it goes to the battery, slowing down when it goes to the resistor, speeding up when it goes to the bat. But what happens is every electron's kind of connected, so they're all really shifting together. Okay. How do you find R? Those were given. Those were given in my problem, Sarah. Okay. Dimon. Okay. Great questions. If you don't like the system of equations, good, because neither do I. There's a much easier way to do it. Stick around to the end of the video. There's going to be a giveaway. All right, we're going to give away the easier method. All right, so that's going to be like the big reveal. I'm just kidding. I've been watching a bit more YouTube just to. I've been curious as to like how to run a monetized channel, and one thing that I learned was the algorithm that suggests videos and like what affects your monetization and like how they suggest your videos is really based on the percentage of your views that make it to the end of the video, right? So YouTube doesn't care if you get like 1,000 views if only like if like 900 of them like tuned out after a minute, right? So what a lot of people do is like, oh, like stick around to the end of the video, I'll give like a code for a giveaway or something like that. I'm not doing that. Let's go over the easier way right now. Okay. So again, I have this, we call it a series circuit, where this is a 2 ohm resistor given, okay? And this is a 3 ohm resistor given, and a 10 volt battery given, okay? Do I use a different, yes, I'm gonna use Ohm's law, because Ohm's law only tells you what goes on inside one resistor, right? So if I want to know the voltage drop across the first resistor, I need to know its resistance and the current going through that resistor. If I want to know the voltage drop across the second resistor, I need to know the current going through that second resistor and the resistance of that second resistor. Luckily, we already knew that the current going through the first resistor, 2 amperes, is equal to the current traveling through the second resistor, which is also 2 amperes. Yes, Sylvie, someone has done their reading. Thank you. Okay, so the first thing I want to do is I want to make this equal to a simple circuit. I want to change this into this, where this is a single resistor that is equivalent to those two. And now we're getting back to part 1 from yesterday, right? Do you guys remember what the resistance of this combined resistor is if these two things are in series? If they're in series, do you know the equivalent resistance, right? You should be looking back at your notes. Let me know what you think. That's for parallel tomorrow. So for series, the easiest thing to do is just to add them. It's that simple, right? So, hey, don't laugh. Don't laugh, okay? No, Yona, it is also, I guess you guys are really, I think the parallel rule definitely is a lot more fun to use and more interesting. But for series, right, you're just adding them, right? So, I go through a 2 ohm resistor, I go through a 3 ohm resistor. that electron just fell to 5 ohms of resistance, right? So this is a 5 ohm resistor. And this is a 10 volt battery, which means in this single resistor, I experience a voltage drop of 10 volts. Boom, V is IR, I is 2 amperes. Super easy, right? Whoa, right? And now that I know that it's 2 amperes, right? I know 2 amperes travels here. So I know in this circuit, 2 amperes is traveling here too, right? So then that allows me to say the voltage drop is 4 volts, 6 volts. Super easy, okay? When you show your work for these types of problems, super important, all right? Here's how I want you to show your work. You're gonna make a chart, okay? This is actually gonna be really fun. A lot of students always compare what we're about to do to Sudoku, all right? If you guys like playing puzzles and stuff, you're gonna show your work with a V equals IR chart, right? So V, I, R. And since I have 2 elements, I'll have 2 rows, but then a third row as well, and this is my total. Okay? So already, what you can do when I'm solving this circuit, if I gain 10 volts, I know my total drop is 10. So my total drop is 10 volts. I also know my resistance for the first one is 2 ohms, and my resistance for the second one is 3 ohms. I also know my total resistance is 5, and my current is 2 amperes in that circuit. V equals IR, okay? That's how you can always check, right? A cross should always follow Ohm's law. I also know that this resistor and this resistor, they both have 2 amperes running through it. So this is 2 amperes, 2 amperes, and then boom, this is 4 volts, boom, this is 6 volts. Pay very close attention to why I labeled total in parentheses, in quotation marks, okay? This is because it's not adding, all right? So it's true that 4 and 6 add to 10, and 2 and 3 add to 5, but 2 and 2 don't add to 2, right? What I mean by the total, this is the row for the simplified equivalent circuit. This row refers to this circuit. It's not anything to do with these 2 things and adding them, all right? That's the big no-no, all right? Please, please, Mr. Ross, please timestamp this, all right? The total is not like adding total, all right? It is not. That's the biggest thing, right? This total row represents the voltage drop across my one single equivalent resistor. The current is the current running through that singular resistor, and this resistance is the resistance of that singular resistor. All right? This is going to make a lot more sense when we move on to a parallel circuit. Ooh, ooh, ooh. So get pumped, okay? Who's pumped? Tell me in the chat who's pumped, okay? And this is the last thing we'll go over. Who's pumped that this is the last thing? Yeah, now you can go eat lunch or play Minecraft or something. Atun, you weren't supposed to say that. No, I'm sad. Thank you, thank you. So let's take a look at Let's make it let's see. Can you draw this, please? A parallel circuit. You can draw this, or this. I don't mind either one. We should know that they are the same thing, right? Okay, so I'm going to make this a 9-volt battery. This is also a 9-volt battery. I'm going to make this 3 ohms. I'm going to make this 6 ohms. 3 ohms, 6 ohms, 1, 2, 1, 2. Okay? The first thing you need to do, right? The very first thing you need to do is to make the equivalent circuit. So either one of these, whichever one you picked, right, is going to equal, right, a 9-volt battery connected to a single simple resistor. All right. Now we're going to use the other formula that Itamar and Yona were doing. Can you guys please find me the equivalent resistance for this parallel section? All right. What is the resistance? Remember, it should be less than 3, no matter what the answer you get. Your final answer should be less than 3, right? I'm going to do it by hand. All right. So it's a race. All right. Whoever gets it first wins. Oh, I think I won. Never mind. LOL. I win. But I'll wait for you guys. Okay. One half. You guys are close. It's not 1/2. Remember, it is 2. It is 1 over REQ equals 1 over R1 plus 1 over R2. So 1 over REQ was 1/2. So REQ was 2 ohms. Okay. Okay. All right. Yeah, so now we can make our chart again. All right. Very simple way to show your work. V equals I R. Oh crap! Why am I doing that? It's V I R 1, 2 total. It's not a real summation total. All right. Oh, look at that interaction, Itamar and Sarah. Right? It's almost like we're in class and you're thanking her in person. Oh my goodness. Oh, my heart. Be still. Okay, so yeah, let's go over the givens first, right? I know I have a 9-volt battery, so let's take a look at my total, right? So if I gained 9 volts, I lost 9 volts. What was my total drop in voltage? 9 volts, right? This is not the battery. Not the battery. This is the drop in that resistor, okay? I also know its resistance. I know them. This is 3, 6, 2. Again, this should serve to remind you, this is not adding those resistors anymore, right? Right? Yeah? Okay. from here, there are a lot of ways we can go. All right. Since I know this is 9 volts, I know that I lose 9 volts there. Look at the loop rule. Do the loop. It's a new dance. All right, do the loop. I think this is actually a real dance already. So maybe do the loop. All right. That should be your dance in senior prom next year or something. Okay. So let's do the loop. I gain 9 volts. I lose 9 volts. Wow. Okay. Or I gain 9 volts. I lose 9 volts. Wow. So through both resistors, I lose 9 volts. So 9 volts, 9 volts. Oh my goodness, what are you noticing? This is not a summation of these two, right? Okay. Then I should be able to tell me the current, right? So this current is 3 amperes. This current is what, 9 equals I 6. This is 1.5. Right? So that's 1.5. And if I have 1.5 amperes this way and 3 amperes this way, how much current do I have when they come together at that junction? What's the current if I have 1.5 amperes and 3 amperes? Someone in the chat. I'll answer Itamar's question very soon. 4.5, right? So this is 4.5 amperes. And oh my gosh, didn't this have 2 ohms? And didn't this have, oh, that means this has 4.5. Oh, wow, it makes sense. So you could have found 4.5 due to using either Ohm's law this way or by adding it through the junction rule this way, right? Can someone answer Itamar's question for me, actually? Oh, Dimon already said so, right? So Itamar, I would say only elements in series do they share the same current, right? As soon as I have it in parallel, the current's splitting, right? My 4.5 ampere current is splitting, and I have no idea how it splits, and they definitely don't necessarily have to get the same current, okay? So I basically shown you how to do like a basic series circuit, all right? I've shown you how to do a parallel circuit. Okay, oh, actually, parallel, the series was on this half, wasn't it? Yeah. So this is a series, all right? Screenshot this if you want. This is the parallel, cool. And I will now upload the worksheets that I wanted you to do by today, and I'll do that today. They will be due Monday, all right, and we will go over them. They'll be due Sunday night, and we will go over them Monday, and then we'll have stream lecture Tuesday, and then we'll go over answers Wednesday. That's what next week is going to look like. Yeah, Dimon, you're still doing the homeworks in class because home is class now. Good one. All right, so if there are no other questions, then I don't want to take up any more of your time. And I will see you tomorrow at 10 a.m. I'm deciding between 2 different shortbread cookie recipes. All right, and we can cook together or something. I have no idea, right? We'll just play it by ear. I would do it on Zoom, except I've heard some really shady things about Zoom and its privacy settings and what you're doing with your data. But I think there must be a way for you to like change your privacy settings so they don't do like sus stuff with it. So we'll see. Yeah, Chris, that's what I'm saying. What's up with that like ratio? I don't know. But I don't do this for the likes, right? I do it for you guys. And with that, I will say goodbye. See you tomorrow, everybody.